So we need to solve this problem. So I've tossed a coin, you all know what that means, yeah? Flipped a coin up, catch it, the heads or tails, right? What's the chance of getting a head on a coin? Toss a coin.
1 out of 2.
1 out of 2. Simple. Right? And then you roll a dice at the same time. So you toss a coin, record, and then you roll a die, you record the results. And it says, what's the probability of getting a head and a prime number? Okay. So what we need to do is the same thing we did last lesson, was look at, well, what is the most important thing to work out first when you do probability? You need to know what?
The amount of outcomes.
The total amount of outcomes. So that's why we're doing our sample space diagram. So a sample space diagram, or a two-way table, will look like this. So what I do is I work out all the combinations. So I can get a 1, a 2, 3, 4, a 5, or a 6. And on the coin, I can get a head or a tail. And I do, so this is a bit more of a simpler case than adding up the scores on the dice that we did before. Right? So, we've got all of that sorted. I'll let you draw it down. Done? So we've done the problem now. We've got an answer of 3 out of 12. Would you like to explain to the millions of people that log into St George's Maths channel and listen to your voice? No? We get that then, yeah? 3 possible options out of the 12 possible options for a head and a prime number. Such a shame, we've got such a celebrity like you. We should give people the benefit of your voice. So 3 out of 12, fine, yeah? Everyone alright with that?
Mm-hmm.
Right, I've got an issue then. I've got a problem for you to think about. We've got this table, two-way table. What if I introduce another thing into the mix? And I say to you, well, I've got the coin, I've got the dice, and I'm going to have a spinner. Do you know what I mean by a spinner?
In poker? No, not
A
in
roulette wheel.
Yeah.
Not quite. Okay. A spinner. So we'll have a look at problem 2. What if I have my coin? So I've got the head on there and a tail underneath. Okay. I've got my dice, or my die. Okay, so I've got a 1, a 3, there's my dice. And then I introduce a spinner from the top, and I'm going to have it a nice, easy spinner, cut into quarters, and I'm going to say that I have red, green, blue and white. Okay. So a spinner, you know, has an arm on it, and you spin it, or you spin the spinner and it lands on a particular colour, and that decides what you're doing. It's like a different version of a dice, decides what you do. You can have numbers on it as well. Okay. So if I then said to you, what would be the probability of getting a tail on the dice and a, let's say, an even number and green on the spinner?
You can do it with this diagram because there are only two things.
Yeah.
You need another diagram.
Well spotted. We can't do a two-way table when we've got three things. So we need another method. What do you think that method is going to be?
Tree diagram.
A tree diagram. Now, a tree diagram is not a three diagram spelt wrong. You can use it for 2 events, 3 events, 4. You can use it for any number of events. A two-way table can only really be done for 2. Makes sense, doesn't it? Okay. But we need something for 3 events in this case. So we use what's called a tree diagram. Right? So I'm going to show you a tree diagram for this. And we have to consider branches and all the possible outcomes. Remember, the most important thing is all the possible outcomes. Now, you can make a tree diagram overly complicated, or you can draw a tree diagram very simple and give you exactly what you want. And what I mean by that is this. So a tree diagram starts at a point and you draw your first 2 branches. Now, the 2 branches, in this case there's only 2, because they are the outcomes for event 1, which is tossing a coin and we get a head or a tail. Alright? Make sense to you?
Mm-hmm.
So we get a head or a tail. Now what we do is we say, right, what happens with the dice? What could happen with the dice? Well, I could have got a head, and then what could happen? I could have got a 1, a 2, a 3, a 4, a 5, or a 6. So don't draw this yet. What I could do is have 1, 2, 3, 4, 5, 6 branches, and then I would need the same 6 branches here. Can you explain why I need 6 on both, Hannah? Or is that a question?
Yeah, question.
A question.
But why? Because right now we're working out what the possibility of a tail and even and a green. Wouldn't you just do 3 because there's only 3 even numbers on the dice?
Oh, I thought you were going to give me a really sensible comment, which you have, a sensible question, but a sensible alternative, which was going to be spot on, but
Yes,
you didn't quite get there. You're almost there, but I can put 1 through to 6 because there are 6 numbers on the dice, so I could have got a head followed by any of these numbers.
Yeah.
The trouble then is, though, what happens after a number on the dice? It has to be, for every 1, I then have to have
3.
4. Can you imagine how complicated this tree diagram is going to end up if I do all of that?
Yeah.
But that would list all possible outcomes. Head followed by 1, followed by green. head followed by 2 followed by, or sorry, head followed by 1 followed by red, head followed by 1 followed by blue, head followed by 1 followed by white. All the possible outcomes are there.
Mm-hmm.
There must be a better way though, obviously. So we don't need to consider all these options. So I can touch my rubber because it's under. So I'm going to redraw this. So this is okay, but impractical. If I spelled that right. You could do it, but it wastes time. So because you didn't draw that, let's draw a better idea for it. Okay. So first of all, let's consider what you've still got, heads and tails. But what could we consider after the heads or tails? Hannah, what are you doing?
You only do it for tails because you're trying to find the possibility of
Okay,
probability.
so yeah, we could just say, let's stop there, let's not bother with our tree diagram. I'm not going to. You could in the future, but I want to show it to explain to you the full thing. Okay? But yeah, we could at one point just stop, not bother with heads because we only are interested in tails. But what could I do afterwards? It's what I'm considering here, even number. I actually only need to consider what? Not 1, 2, 3, 4, 5, 6, but
2, 4, 6.
Yeah, sort of, not quite what I'm thinking of.
1,
Yeah,
3, 5.
Because 2, 4 and 6 are all what? What? They're the even numbers, and then the other numbers are
Prime.
Odd.
odd numbers. So what if I were to just write even and odd here? Because actually I don't care about the numbers individually, I only care whether they're even or odd. Okay? And suddenly then I've got,
But why do you do it for heads as well?
well, like I said, I'm just explaining, I'm doing a full tree diagram, but like you said, we don't need it, but I'm going to show the full thing to start with. Okay, Ewan.
And then do you do green, not green?
Perfect. Spot on. You're getting there. Right? So after this, I'm just going to do green and not green. Spot on.
But that doesn't tell you how many isn't green, and it doesn't tell you how many are odd and how many.
Well, we're going to get to that point. Again, good point made. But I'm going to do green and not green. Green and not green. Again, there's more options than I need. Sorry, green and not green. But what I'm showing you here is how you can do a tree diagram, right, and make it a lot simpler. Now, think about a tree diagram. Quite often in a question, the tree diagram is already drawn for you, but you have to fill in some missing things, and we have to fill in the probabilities of each thing. So this is where we now consider the fact that not green is actually 3 different colours. So we put the probabilities on the branches. So what's the probability of getting ahead?
1, 2.
1 out of 2, 1 out of 2. What's the probability of getting an even number?
1, 2.
1 out of 2, 1 out of 2, 1 out of 2, 1 out of 2. The reason why it's 1 out of 2 is because each set must add up to what? 1. So each branch, where it branches off, should equal 1.
But green and not green doesn't do that.
Well, it does.
1
What's the probability of getting green?
1/4.
1/4. The probability of it not being green?
3/4.
3/4. Good. And both of those add up to 1. Okay. So we've got 1/4, 3/4, 1/4, 3/4, 1/4. They're the same for each type. Okay. Now, what was it we needed to work out? What is the probability of
Tail, even number in green.
tail, even number green? So we have to work out the path route that we have to take.
Yeah.
So the path route that I've got to take is
Tail.
tail,
Even
even number,
and green.
and then a green.
And yeah, I know what to do.
That's the root we need.
We have to look at how much it adds up to. So 1
Right,
quarter.
not quite yet, no. See, when we go this direction on a tree diagram, we are saying tail and even and green. Now, do you remember from before what the word and meant with probability?
A second outcome.
Yeah, but in terms of a mathematical operator, anyone remember what I said? No. Well, the word and relates to multiply. The word or means to add with probability. Do you remember when we were doing what's the probability of getting a 3 or a 6 on a dice? You added those together. But when we've got this word and, so when we move this way, we have to multiply. So we have to do, in this case, we've got tails multiplied by even multiplied by green. So that would be 1/2 multiplied by 1/2 multiplied by 1/4. And the answer is
1 out of 16.
1 out of 16. So that 16 should relate to how many possible outcomes there are
Mm-hmm.
when you consider just odd and even and green or not green.
Are there 48 possible?
Pardon?
Never mind.
Mr. Watson, can we do the tree diagram more shorter? What's the maximum possible?
Shorter? What do you mean shorter?
Smaller. Because you said it's
Well, we've got to have 3 things because we've got 3 things happening. Now, if I say to you, now guys, to extend it a little, using that same tree diagram, so you don't have to rewrite things, this is why we did the full tree diagram. What is the probability of getting, okay, a head and odd and red, or sorry, I shouldn't have had a bracket there. That bracket shouldn't be there. Head and red, head and odd and red, or green. So head and odd and red, or green. Now green means every possibility. Alright? So green at the end. So you could have had a head and odd and even, green, tails and... So, work it out. I want you to... You can't do it straight away. If you've got a question, what's the question?
If you use this tree diagram but you replace the red with... So you replace the red with green like we just did. And then would you just add another quarter?
Well, we'll have to change the tree diagram a little bit, won't we?
Yeah, but would you just add a quarter where because it's 1 out of 16, would you just times it by another quarter?
But this is head and odd and red. Just not just times it by another quarter. No.
But if red is another quarter...
Now you've got a lot... This one here, this green, adds lots of possible options. I need you to reconsider. You? I don't want that. You haven't... It was far too quick. So we've got to adjust this tree diagram a little bit. So... head and tail. The next one would be odd and even. What has to come next though?
He will be red or not red and green or not green.
No.
No, red and green.
Red and green and
Not red and green.
Not red.
other. Yeah, we can go with that.
But
So
why?
we have to have 3 options now.
But we don't need and red and green. We need only one. So why?
Red, green. So we have to have them separate.
Nah.
Yeah.
Can you just do 1/16 and then 4 means plus. So plus the
Well, no, because the green, you'll see why in a minute.
Red and green
other.
each are equal to a quarter. Other is equal to 2 quarters,
What
which
is-
is a half. So technically, red and green are equal to a half.
So
So
it says and red or green. So you
No,
can
right.
put them together.
I've kind of, this is a poorly written question, I guess. Head and odd and red, or whatever else with a green at the end.
head and
So that's the
odd
thing.
and green.
So let's consider our options. We have to have a head followed by odd followed by red, or greens, which means we've got to go these routes as well. So it's not quite as simple as just, so you have got to consider head odd red, head odd green, head even green, tails odd green, tails even green.
What about the other reds?
Well, we're not interested in red unless it comes after a head and an odd.
But
It's like saying, right, let's play a game. We've got 3 things to do. You win if the spinner lands on green. Doesn't matter what else happens. If the spinner lands on green, you win. If the spinner lands on red, you have to have got a head and an odd on the other 2.
But how come the head and the odd don't apply to the green?
Because that's what I've just said. That's my issue. Yeah.
Mr. Boss.
Okay.
So regardless of what the other 2 do, if you get a green, you win. Yeah?
Okay.
If you have a red, you have to have a head and an odd with it. If you get one of the other colours, you lose completely.
Mr. Boss.
Right? So other, lose, other, lose, other, lose, other, lose. Red followed by an E, you lose. Red followed by, yeah, you lose. You win. So you always win if you end up with a green. If you get a red, it has to follow that. Yeah.
But we need to multiply, and a green we have to plus because it's over.
No, right, so we do half, half again. Half, half. Half, half. Okay. Red this time is a quarter, and this is 2 quarters. We'll just write the ones we're interested in now. Quarter, a quarter, a quarter. Right. Okay. What is the result of this one? It's a half times a half times a quarter, which we know is 1 out of 16. Now, the nice thing about this is a lot of them are the same. Well, they're all the same, aren't they?
Yeah.
Half, half, quarter. So actually that one is also going to be a 16. Half, half, quarter is also going to be a 16. Half, half, quarter is also going to be, they're all 16ths. Okay, each branch is 16ths. Now what do we do? Now we add them. Okay, and we get the answer 1, 2, 3, 4, 5 over
16.
16. So that's your answer.
So hard. Would you give such this at the test? A lot or one?
Why are we talking about a test that's not even set and isn't going to be for like a month or so? Stop working to test.
We're not having.
Hey?
We're going to do this for a month.
No, we're not going to do a test.
On it.
Well, you've got ski week, another week, 3 weeks of holiday. That's 5 weeks. Then let's say I'm not going to give you a test for 3 weeks back. That's 8. It's 2 months before you're going to get a test.
Do we have another week after teacher?
Yes.
Yeah.
1 week.
Oh, you must have
Okay. The difference with this. Oh, big sigh.
Wait, there's only 4 outcomes, right? A girl and a girl, a boy and a girl, a girl and a boy and a boy and a boy.
Yes. There are 4 outcomes. However, this is an example with Ewan and his disappearing children of dependent probabilities. Okay, because when the children disappear outside the door, that changes how many people are in. So what was the probability of the first person being a girl?
1, 2. Ah, no, 9 out of
9 out of 17. What was the probability of it being a boy?
8.
8. Right, now here's the thing. I'm only going to tell you one more because you're going to finish this off for yourself, for homework. Okay? Just going to tell you. Right, I'd write this down rather than writing the agenda just yet. What is the probability of the second person being a girl?
8 out of 17.
No.
One.
Why? But you took 1 girl out.
Exactly. The 8 is right. Don't simplify. 8 out of 16.
Ah, yeah.
Because you're right, a girl has gone, but a girl counts as a person. So there are only 16 people left.
Yeah.
What
One out
then
of 2.
is the probability of it being girl-girl? This doesn't solve our problem. What's the probability of girl-girl? Girl and girl would be 9 over 17
Plus.
times
Oh.
1 over 2.
8
1
out
over 2.
of 16. Or 1 out of 2. Now you're not interested in that. You're only interested in girl, boy, boy, girl. So when you come back to me, solve that problem.
Mr. Boss, but boy, in this, it will be 9 out of 16. Yeah, but
And there are only 8 boys.
it will be 8 out of 16.
Next time we see.
This is we haven't